results out of the project were a data scraping tool for the internet was written and collected data and what that implies about the source of the data and reliability and so forth. And then the last presentation will be about what that implies about teaching in PA or public policy programs. And I think we've got a great and diverse group of presenters today. Trevor Self from the IMF is going to lead us off, followed by Minyoung from SUNY Albany. And then the third paper, which will be about the data scraping, is by Evgeny Klochikhin from the American Institutes for Research. And then finally, Dahlia Remler is going to finish us off in terms of talking about teaching implications. So the way we're going to do this is we've tried to ask the authors to limit themselves to 15 minutes, but no more than 17. It's at their discretion if they'd like to take a question or two, but they will be held to the 17 minutes, so we can leave roughly 20 minutes at the end for some broader discussion or question. So Trevor.
Sure. Thanks very much, Ken. My name is Trevor Self. I am a program manager at the International Monetary Fund. I'm a program manager for organizational development and evaluation. And that brings me to the first point that you probably raised, and that is that I'm here today just in my personal capacity, so please don't construe anything I say as representing just use the IMF for its member. Okay. You get the impression that's sort of boilerplate. So I imagine you're probably here at this talk for the same reason I wanted to come to this talk, just to find out what big data is. And so I thought we might start off with a couple definitions. And the first one, is probably the best one I know of, captures maybe not so much the definition itself as the gist of what goes on around in the conversations about big data. You may have seen this. So in case you can't read that, big data is like teenage sex. Everyone talks about it, nobody really knows how to do it, everyone thinks everyone else is doing it, so everyone claims they are doing it. So there you have it. Now you know what big data is. Or are. I'm still not sure about that. In most definitions of big data, you come across these notions of it being somehow associated with really high levels of volume, velocity, and variety. So you're given with large quantities of data that come through very quickly and from very different types of formats. And I should pause here and say that I think some of the other speakers are going to talk a lot about the promise of big data, where it might go, and the types of things that we can do with it that are very useful in public policy. And I agree with the things that they're going to talk about. But I thought we might start off more in this talk about some of the theoretical concerns, the methodological concerns, and maybe what I'm doing is kind of tapping the brakes a little bit on jumping on the bandwagon. Okay, so the first thing I want to talk about then are some of the implications of defining big data in that way. So the first thing, and I should mention, I have far more concerns about big data than will fit in the narrow amount of time that we have for these talks, so maybe it'll come out in the questions if I'm not able to cover everything. But I think my biggest concern is about inclusion. The kinds of people who produce the data exhaust, so to speak, that ends up being scooped up for big data analyses are not necessarily representative of the populations that we serve, of the entire constituency. You may be familiar, for example, with the Boston app, the Street Bump app, where you have a smartphone app, and you drive along and you hit a pothole, it senses it on your smartphone, and the city says, oh, there's a pothole there, they go fix the pothole. Well, you end up very quickly fixing all the potholes where the young, affluent people live, and not the potholes where the older and less affluent people live, and in some of the industrial areas. So perhaps particularly coming at this from an international point of view, where there are great disparities on who has access to creating these sorts of things with their online sales and purchases, with tweets, social media, whatnot, of creating that exhaust. I think it's very important to keep in mind you're not capturing the entire population of who your entire constituency might be. And the second one is related to legitimacy. If we begin to transition public policy into a vernacular of big data, that could be good. It could have very positive outcomes. But we need to be cautious about who loses voice when we do that, because not everybody has access to creating big data, to being able to store it and manipulate it and represent it in the public place. So I think there are questions if we begin to say the only kinds of legitimate evidence are big data evidence, and we start weighting things according to sample size instead of according to the value of the evidence. So these are if you don't get anything else out of this talk, I hope you get that main point there. I also think it's interesting to define big data the way that many people do, as somehow being associated with the how difficult it is, how onerous it is to deal with it. So we say, well, if it's really big, right? If you can't store it all in one place, if you can't analyze it all in one place, if it's really hard to deal with, then that's big. That seems odd to me because this is not a new issue. This is technology has always had a reciprocal relation and a cyclical relation with our capacity to deal with the information that it creates. So you could go back all the way to cuneiform and being able to represent numbers in a particular way, and that opens up new horizons of mathematics, and you create an abacus, and that it keeps going on and on and on. But this is not a new thing, so I think it's a bit odd to kind of draw a line in the sand and say, well, now is when the data are really big, and we need to change all the rules. I'm not sure that there's a big rule change that's needed. You may hear people who are major advocates of big data talk about improving information quality or decision quality, and that's what this should be about, is improving decision quality. But decision quality is a function of information quality, not information quantity. And all things equal, I would rather have much less information than more, because there's less to go through. I would rather have really high quality information for the amount of quantity that I'm dealing with. And I think this is a major point that's missed in a lot of the big data discussions. So if you're just generating more quantity, as Stalin is often credited as having said, quantity has a quality all its own. If that's what you're relying on, you may be driving down the overall information quality that's leading into the decisions, and you're having to sift through more gunk than it's worth. Some advocates also will say, well, as long as we just show that there's a correlation, as long as I know that if A and B happen, and C is going to happen, I don't need an explanation. That's sort of dust bowl empiricism. In public policy, explanation usually does matter. There are two situations in which it doesn't. One of those would be if you just don't care what the consequences are of meddling with these things. That's rarely the case, I hope, in public policy. The other one is if you're just reacting to the data, right? If you can't go out and influence these variables, these phenomena in life, and you're just reacting to them, then perhaps it's enough to stop at prediction. Description, prediction, explanation. If you want to stop at prediction, for example, from my own work, there are weather patterns in the southern Indian Ocean that end up predicting drought patterns in southeastern Africa, right? And if you're working in the areas of food policy and water security, then that's very useful information. And if you're just trying to predict how it is that you're going to cope with the upcoming drought, fine. But the moment that you step in and you say, now I'm going to intervene there, right? We're going to try to do some geoengineering. We're going to have a bunch of really big ships go in a clockwise circle to try to counteract the motions in the Indian Ocean in order to, whatever. The moment that you put your, the monkey wrench in it to try to make things work how you want it to, then you do need explanation. If for no other reason than to be able to substantiate it to the constituency, right? These are people whose lives are being influenced. And if you just come in and say, well, the big data said so, I read the chicken entrails, and there are a lot of entrails. That's not really a substantive argument to make to the people that we're supposed to be advocating for. One of the common claims about big data is that, we just want to get back to the data, we just want to let the data speak for themselves. And I want to, if any of you have this, I want to disabuse you of the notion of raw data. There is no such thing as raw data. Data are as theory-laden as any other thing that you can observe in life, right? So when we talk about big data, we're talking about already having picked what we're going to measure, what we're not going to measure, who we're going to measure, who we're not going to measure, how we're going to measure those things, how they're going to be analyzed, everything. So the idea that somehow this is you hear the term, the view from nowhere, is a myth. And it's important to realize that we have a role in those data. And the data don't speak for themselves. If data spoke for themselves, we wouldn't need analyses, right? We could just stare at a spreadsheet and listen to the faint murmurs of truth, right? But that's not the case. The data don't speak for themselves. We have to collect them. We have to interrogate them. I also want to kind of group these together. When I say the data are not the domain, or this notion of fetishizing data or of data worshiping, we can begin to think that the numbers just kind of exist on their own. Right? that this is somehow the ultimate version of what evidence looks like. But evidence and data are not the same thing. And, excuse me, springtime in DC. It's easy to get caught up in believing that you're just talking about the data, and if you can manipulate the data enough, that's the representation of the real thing. And the danger here is that you distance yourself from the actual phenomenon. And you lose sight of being able to say, well, we're not capturing everything. It's easy to believe when you're swamped with that much information that you're looking at everything there is. And in most cases, you're not. And even if you're one of the people who says, oh, well, N equals all when we're dealing with big data, that's nonsense. Because when you're dealing with public policy, you're not talking about making policy for the data that just existed. You're talking about making policy that's going to influence the data that have yet to exist. You couldn't capture future data yet. So there's a real danger here in getting at this notion of fetishizing data. Ideally, we wouldn't use data at all. Data are rudimentary representations of phenomena out in real life. And they are a way that we translate crudely how these phenomena fit together, and we group them, and we say, okay, we're going to analyze them in these ways, and then we have to translate back out of data back to phenomena, right? So ideally, we wouldn't want to go through this double translation. We would rather just talk about the phenomena and analyze the phenomena. And related to that is this notion that technology might save us from having to make some of these decisions. This, too, I think is a pernicious idea. That somehow we are saved from having to make some of the difficult decisions about how to value this or whom to include and so forth, if all we just do is put everything in the blender, right? And that's not the case. In its worst form, what big data does is to obscure the very things that we ought to be paying the most attention to hide the theory. So when people say, oh, big data is theory-free, it's not theory-free. Often it just hides the theory. And in the best versions of public policy, what we ought to be doing is bringing controversies to light and dealing with them in a way that there are multiple forms of data that we can assess those things and resolve the controversy, rather than subduing that controversy and just kind of saying, well, the data resolved it as though it's some sort of political cudgel. Just the last couple points before I want to go into some recommendations for curricula. There's an associated term of data science. I'm not sure what this adds. I've mentioned a couple times that many of these things or these issues are not new. And I don't know that we need a new field for this. And the term data science makes as much sense to me as talking about microscope science or telescope science. Data is just a way that we deal with information. So if you want to talk about life science and physical science, what you're talking about is science, and just a pause here. I'm talking in a strict Popperian sense, using empirical tests of falsifiable hypotheses, right? Two components, empirical tests, falsifiable hypotheses. Nowhere in there is data necessarily, just evidence. But for life science or physical science, what you're talking about is applying that epistemology to questions about life, or applying that epistemology to questions about the physical environment. Information science is applying the epistemology of science to questions about information processing. Computer science, same thing. So the notion of data science, the only way that makes sense to me is if we're talking about applying the epistemology of science to data, in which case, shouldn't that just be under information science or computer science? So again, I think this goes back to somehow building data up as something that we just go worship without really considering what we're talking about. It's just an intermediary. All right. If you've looked into what does 4 mean? 4 minutes left. Okay. I thought you were rating me. Whether I go on the lower rating. So if you've looked into big data much, you'll probably realize that one of the real risks is overinterpretation. It's easy to look at that huge deluge and say, that's the weight that I should give this data. But again, going back to one of my earlier points, there's a difference between data quality and data quantity. Okay? And it's very easy to look at some huge mass of data rushing through and pay no attention to your cumulative type 1 error. I don't know who's a statistician in here and who's not. But you're going to find some very spurious effects over and over and over again if you just have that quantity of data. And it's very easy to say, well, and then on top of that, we have so much statistical power that we're really certain it's there, right? The effect size might be minuscule, but you're very certain it's there. Some curricular recommendations very quickly. I've tried to prioritize these. So if you're thinking about addressing big data in curricula, I would suggest these things. First of all, focusing on big data to the extent that it contributes to good governance, right? That should be the end goal. If you're talking, I think there's a real risk of talking about big data in terms of statistics first or tools first, even worse. But I think the real emphasis is on interpretation, that the most important thing is being able to interpret it. And then it's on the methods, which are more important than the statistics, which are more important than the tools. So if you come into it talking about, well, here are the tools, here's how you use the tools, and by the way, here's some statistics, and you've got so much in, you don't even have to worry about methods and interpretation. I think that's going at it exactly backwards. I would suggest that you consider just a framework of thinking about data in three main types. One type being exploratory, or sort of a source of serendipitous events. So this is hypothesis formation. Then you have another that is disconfirmatory, not confirmatory. So this is, well, we get the idea for how things might be going on, and we might be able to make a policy that addresses that. This is where you test it, and this is where you then kind of create a dashboard to put those ideas in place if they work. Obviously, hopefully you're already doing all of this, teaching things like threats to validity, cross-validation. Cross-validation obviously isn't going to save you if you have sampling problems. And ethics. Many of these issues, as I said earlier, have been covered by by many fields for decades. So, you can draw on many other fields, and just to come back to the data science thing, I think there's a danger when we create new terms and new fields of saying, we've created these because new rules apply. The old rules don't apply anymore, right? So I think it's important to connect these back to existing fields and have decades of very useful research on these issues. Big data is very similar to running meta-analyses. So if you want to teach people how to do big data analyses, I think meta-analysis is a good place to start. It's just that the consequences of doing big data badly are much greater than running meta-analyses badly. Things like multi-trait, multi-method analyses, measurement theory. If you teach people structural equation modeling, I think it gets at some of the measurement issues. And just very, very briefly, I'm not going to spend much time on these. I know I've got about 30 seconds left. So there are all sorts of crazy comments, and I think whatever you do in teaching big data, disregard this nonsense. This is just garbage. Right? It's trash that needs to be taken out, and I don't think we should give it much countenance at all. And when you read this kind of stuff, I hope that it leads you to having the exact same kind of response that I think Karl Popper would have. Sir Karl Popper reacting in the way that I think that he would to some of the epistemic claims of big data proponents. So I hope you have a similar reaction. And then last but not least, I'll finish with the immortal words of Spider-Man's uncle, Ben Parker. With great 1 minus beta comes great responsibility. Thank you very much.
Trevor, thanks for the great lead off. And so now we'll have Minyoung.
Yeah, so if you just start talking, and then whenever you want to progress it, just hit the right arrow.
Okay, thank you. Hello, my name is Minyoung. I'm a doctorate candidate in public administration at the Rockefeller College of Public Affairs and Policy, University at Albany. If we're talking about my paper, I have to reveal my identity. Actually, I'm big data proponent. So, so maybe some ideas in this paper may have some conflict with Trevor's arguments. Actually, this paper was written by me and my co-author Minyoung. Actually, he is my younger brother. He is also a doctorate candidate in computer science, Gangneung University in South Korea. So actually, he has been engaged in a really big data project for South Korean government. So actually, while he is working, worked for this project, we have been, developed this idea. Okay, before talking about my paper, I'd like to introduce what I'm going to do today. So I'm going to briefly introduce, what big data is, actually, my understanding and my younger brother's understanding, and what big data management is. As far as I know, there is no attempt to define big data management from managerial perspective yet. So we tried to define what big data management is, especially in the public sector. And we actually came up, in this paper, actually my younger brother and we came up with this 4-dimension model of big data management. And actually we discussed issues and challenges in big data management by this 4-dimension model. And to satisfy my audience from educational area, I actually briefly introduced what implications we can get from my paper, especially for MPA and MPP programs. Actually, I'm teaching MPA students at the Rockefeller College in a course. The course name is Data Models and Decisions. So I'm thinking that I can get really interesting implications from this paper. In 2012, the Obama government announced that they would invest more than $200 million in big data R&D initiatives. Actually, according to a study, currently federal agencies are managing over 150 big data initiatives, and their spending is expected to be increasing up to $7.2 billion by 2017. But compared to the size of big data initiatives, it seems that our understanding of big data is quite limited yet. Okay, let me talk about what big data is. Actually, there is no consensus on what big data is yet, but basically, as Trevor said, there are many arguments that basically big data should have those three components: volume, variety, and velocity. So I'm thinking, because Trevor, explained about volume very well, so I just want to talk about variety and velocity of data. 90% of existing digital data in the world is unstructured data. So actually, we are really good at dealing with structured data. So, but the matter is that how we can deal with those massive unstructured data is really matter. So, and the other aspect of big data we have to care about is that the velocity. The speed of being generated is so fast. It's growing every single year. So 90% of existing data in the world has been created in the last 2 years alone. That's really big. Actually, so far, many efforts about how we can deal with and how we can harness big data has been done in computer science area. But I believe that actually my younger brother, so even though he is a computer scientist, but we believe that actually the rise of big data is not a technical phenomena, but a socio-technical phenomena. So we have to build some ideas about from managerial perspective, and we have to ask computer scientists to develop something we need. So we actually try to define what big data management is. So we define this term like the whole effort of an organization to generate, collect, store, organize, process, retrieve, analyze, and share large-scale data in diverse forms, which are generated by various sources in real time or near real time in order to create values. Okay, let me introduce the four-dimension model of big data management we came up with in my paper. We believe that there are 4 basic dimensions of big data management. The first one is technical dimension, second one is data dimension, third one is managerial dimension, third one is bigger political dimension. Actually, Trevor said that data is not the domain, but actually my younger brother and we believe that data should be the domain in this era of big data. Okay, let me start with technical challenge first. I believe that many audience are not from engineering or computer science area, so I just want to briefly introduce some arguments in technical aspect. Big data data, actually we have to think about how to collect big data and how to clean, how to store, and how to process and analyze big data. To deal with all the steps, all matters, like the collection, cleansing, storage, and analysis. Actually, basically, we need high capable computer processing systems and large bandwidth networks. Especially, when it comes to from a social scientist perspective, I'm thinking that we need to pay more attention on data cleaning and data analysis, because we believe that computer science, they can provide us with clean data, even though they are not structured. But actually my younger brother, he is studying cloud and computing system, but he said that actually there is no standard for levels of data cleaning techniques and cleaning dedicated computer systems. So from computer scientist perspective, it is really hard to figure out how much accurate cleansing dedicated computer system they have to provide for social scientists or for end users. And let me talk about data analytics. Actually, as we know, there is no one fantastic and perfect tool to manage a processing job, especially large, massive data, which came, into the data system in real time or near real time. Okay, I really want, audience, you really focus on data challenges, because actually people believe that technology can solve all the problems we have in the era of big data. But actually, we really need to understand what data is. Even though we have really high extensive knowledge on cleaned and structured data, we don't know well about unstructured data. So 90% of existing data is unstructured data. We should focus on the fact how we can handle unstructured data can decide our future. So data quality, data standardization, data classification, all the things are really important in terms of dealing with unstructured data. Let me talk about data quality first. Data accuracy, completeness, reliability, consistency, and accessibility, interpretability, and timeliness, all the factors are really important in terms of data quality. But actually, as I mentioned before, when it comes to dealing with unstructured data, we don't know how we can guarantee data quality. Data scientists say that they don't know, how much clean data they can have from unstructured data sources. And the other thing is that data standardization. Actually, Dr. Lynch said in 2008 in his article, he said that we need to build community-level standardization. Yes, actually, we are really good at building standardization, standard in small, group of people, like organization or in some sector. But actually, in the era of big data, data convergence, data integration can determine our future. So it means that we need to talk about how we can build the standardization as a community, rather than just an organization, rather than just a social scientist group. And the other thing is the data classification. These days, actual data can be classified by diverse standards depending on what purpose we have in terms of data. But especially in computer science, they can be usually classified by forms, like a structured, unstructured, human-generated, machine-generated, like that. But in social science or in the public sector, we classify data like personally identifiable data or non-personally identifiable data. But actually, by using the two different standards, we can actually manage all the steps regarding the database management, like how we can deal with data in terms of technical aspect, managerial, and legal domains. So we need to start our conversation with computer scientists and social scientists how we can build one big, comprehensive data classification standard. Okay, let me talk about managerial challenges. Actually, to come up with some ideas and arguments about managerial challenges, I reviewed extensive literature on IT initiatives in government and information system management and information management and knowledge management. Actually, my dissertation is about knowledge management. But from the literature on knowledge management, I've learned a lot of lessons about how we can deal with big data in organizations, especially in the public sector. Goal settings and casting visions is really important. Actually, many literature says that without clear and realistic goals, we can be successful. And in terms of goals and visions, we need to really care about how we can make an alignment between organizational and project goals and between goals of different organizations. Actually, when it comes to big data initiatives, collaboration is really important. So it means that we need to care about what other people have their own goals, how we can make an alignment. And the other aspect of managerial challenge is how we can secure, how we can how we can get how we can secure executive leadership, far-sighted executive leadership and support. Actually, people who are engaged in big data management today said that actually they really need far-sighted leadership and strong mid-term, at least mid-term or long-term support. According to the study conducted by the Tech America Foundation in 2013, 26% and 36% invested 1 out of 3 IT experts working in the federal or state government. They said that they have been frustrated with frequent leadership changes in big data management in their organizations. So it means that depending how we can manage human resources and physical resources, actually we can contribute to developing big data technologies in the public sector or both in private sector. Third issue regarding managerial challenges in big data management is about how we can manage resources. So as many already know, public sector has been suffering from the shortage of IT resources and IT infrastructures and expertise and data scientists in the public sector. So we need to really think about that. Public organizations or other institutions, they should contract IT services out to the private sector, or they're gonna just to develop and use in-house resources. There are many controversies of the pros and cons about pros and cons of outsourcing IT services to the private sector or using in-house resources, but I'm not going to briefly, I'm not going to talk about the pros and cons in detail here. But just I want to mention that we really need to think about what is the best strategy, because the scale of data we have to deal with in the era of big data is different from the conventional ones, right? So it means that in big data we have a lot of chunks of data which can have can affect to information privacy and data privacy. So we really need to come up with another, discussions and ideas about how to manage data, how to manage resources. And the last part of managerial challenges I want to talk here is about organizational culture. Actually, conventionally, we make decisions on the basis of intuitions and personal experience. So McAfee and Jolson, actually in 2012, they thought that these days, actually so far, many organizations in both public and private sector, they are really, they have decision-making habit, like we really love making decisions by hippos. It means the high-paid person's opinions. So to form the culture that we make a decision on the basis of rigorous evidence rather than intuitions or experience, we need to think about how we can build a data-driven culture in our organizations in the public sector. So data-driven culture can have some people who are appreciating the value of data and data analytics. So, and the other issue regarding managerial challenges of big data management is that is about how we can build a culture in favor of data and information sharing. As I mentioned before, data convergence, data integration is the core of big data management. So without sharing ideas and without sharing data, we cannot actually reap the full benefit of big data management. The last two challenges can come from legal and political domain. As we know, there is a turf war brewing over information data policy and data breach. So actually, in the public sector, of course in the private sector too, personally identifiable information really matters. So really, even though one piece of data cannot tell anything about individual, maybe the data integration can give more information about individuals. So we have to think about how we can deal with those kind of data convergence, which can have some risk about revealing individual information. And the other aspect is that according to the fair information practice principles, actually to keep information policy privacy, we have to be aware of the knowledge and awareness and choices and consent of individuals. So actually these days, many people, we don't know when our information is being collected. So it means that the awareness of data collection is very declining, and it is really hard to get enough chance. It actually as an individual, it is hard to get enough chances to show and express my opinion whether or not I agree with the data collection. So actually there is a endless conversation and endless discussion over do not track online act. So we really need to think about where this debate will go. And data breach also is a big problem. Data breach notification law and regulation, actually there is no one consensus yet. So we need to really keep an eye on where it goes. Okay, let me talk about if so, what implications.
Can you move on to wrap up? We're kind of over time already. And, yeah, so could you kind of go quickly and finish?
Yeah, okay.
You're kind of
I'm sorry. Okay. So I really want to talk about if so, what we can, what implications we can get for MPP and MPA programs. So this is a chart of this five core competences. So I want to really highlight, that we really need to pay more attention to third and fifth, competencies. Actually, the ability to analyze, synthesize, and critically solve problems and make decisions. So from my experience, while I teach my students in the master, course, I found that many of my students, they have background not relevant to data analysis or, data, any other methodological techniques. So 90% of my students are from the similar domain, social science domain, like political science, sociology, psychology, American literature, like that. So it means that basically their existing knowledge, before coming to MP and PP course, their existing knowledge about methodology and data is very low. So I'm thinking, I do like to really suggest to, MPP and MP programs have a course in which students can learn about data itself and they can play with data. So actually, even though we can offer some courses about methodologies, actually, I believe that because I were a student, for several years, 10 years, so I believe that, actually in many education institutions, they have very small number of courses about data itself, and, in which students can play with data. And I do like to talk about, we actually need to focus on the fifth, competency. Because as mentioned before in the first session, collaboration, soft skill is really important because to make data integration and data sharing, actually we need to have conversation. We need to work with many people from different areas, like computer scientists and data scientists, and from some expert groups in specific domains. So actually having a good skill, we can have conversations and we can make some progress, together. So it is really important. Okay, thank you.
So next we have Edward.
Hi, my name is Evgeny, and I work for American Institute for Research as a researcher. And originally I put in a very research intense and specific abstract as a proposal, but since we had the conversation in the run-up to the session, I decided to do it a little bit broader and use it as a use case, what we do particularly with big data. So the topic eventually is big data in public policy, big question and practical solutions. American Institute for Research is working mostly in education and social policy, and our particular Center for Science and Innovation Policy is a pretty young organization within American Institute for Research, and we focus mostly on science policy and work with federal agencies and with the government. So, one, we do work with big data in our center. Two, we do research contracts and more applied research and evaluation. And also three, we do teach big data for federal government employees. And I will give you a particular example. So the first question that everyone is trying to answer in this presentation is, what is big data? One that comes always to mind is, it is size. It is big data. But it does very much depend on the specific applications. For example, sometimes you could have 100 records that are so messy that they will require so much work and so much tangling around that people call it big data because it requires so much work and processing power. On the other hand, you can have millions of records, and they are so well organized that they're not really big data. You can run some stat analysis or SAS or things like that, which are more conventional, and you won't call it big data. The second parameter that defines big data is new types of data. You go to social media, you go to web pages, you take raw text. This is big data because this is very different from what we were using before that. This is very different from digits that we use in stats. But you have a lot of categorical variables where you have, for example, we work with NSF data entities, NSF division, NSF programs, or abstracts of awards. This is very, very difficult and very different. And lastly, and most importantly, I think what defines big data is new methods and approaches. You don't use only statistics or econometrics to work with big data, but you actually have to develop and optimize new and existing approaches that most often come from computer science, but also can be developed from your econometric background and other things. And one of the major definitions of these new methods is it should be economically viable. You cannot run your task for like a week and then you say, that was wrong, sorry. And it should be performed in an acceptable time frame. So what are the challenges? One, data gathering, and this actually goes a lot to Minyoung. One is data gathering and acquisition. How do you extract information from new sources? How do you scrape a website? This is very important. Then data organization. When you already scraped it, when you have some raw text, where do you put it? How do you organize it so that you can use it for further analysis? So how do you analyze new types of data? What do you do with raw text, for example? And then the last one is data communication, the most important one probably, because that's where you go to policymakers, to decision makers, to your clients, and you have to communicate what you have done with this big data, how you extracted it, how you transformed it, and not using those technical terms like, oh, I used some method from computer science, you never heard of. What skills do we need after all that? One, understand both the root of the problem and the solution. You cannot just take computer scientist, put him in the room and say, I have a policy problem, please solve it. You have to have a social scientist working with computer scientists, or hopefully integrated in one person that will know what is the hypothesis, what is the theory, interpretation, and what is the data and how you can use the data. Second one comes from this one. Combine social science and technical knowledge. Be open, and that's one of the points for hiring policy too within organizations. You have to have two backgrounds usually, which is good. Be open to learn and improve. Never late to start coding. I started coding a couple of years ago because my degree is in public policy, and it's never late because that's where the world is. You have to go with it. You have to collaborate. Don't worry about going to good IT support and asking computer scientists to help you. You cannot know everything. You have to talk to professionals sometimes and collaborate with them. And finally, management. You cannot put IT on as a support function. Oh, I have a help desk, so I don't know, my Windows is frozen, so let me call them. No, they should also help you with more complex tasks because they are professionals, because they have computer engineering backgrounds. And that's how organizational development should go. What are the teaching implications of all that? Well, first, there is in education studies, there is so-called integrated curriculum. This is one of the multidisciplinary approaches to how you can do teaching curriculum at schools. So you do not have to start from scratch. You cannot just, we don't need statistical inference anymore, just throw it away, let's do computer science. You have to supplement things. You have to take what you already have and think how you go from there to the next level and how you can implement or integrate new courses into that. The second one is active learning. Another one comes from education studies, basically, because professor who delivers on knowledge. Just giving facts to students is not enough anymore. You have to learn with them. This is facilitated learning. So new forms of teaching like problem-solving seminars, not case studies, but hands-on dynamic experiences where you actually go into class and work on data together with students. And students figure it out, and everyone will come with their own solution, and that is the most important. There is no one solution to big data. There are several. And finally, there is a lot of open data out there. Just make use of it. Obama's Open Data Initiative is just great. Data.gov. And if you go there, you have a lot of repositories. And actually, in New York University, they have a Gov Lab, which identified 500 companies that are already based on open data. So it's a growing trend. Practical example. So our center currently delivers a course for census and USPTO data people. And this is a structure, how it would look like. So first you have to extract the information, capture the information by web scraping. Then you have to analyze it, clean it, organize it. You can do some networks out of it. Link to census and USPTO admin data, administrative data that comes in when you want some more complex modeling. Then you do statistical inference. Again, this is important, and this is traditional massive. So it's important not to throw it away. Longitudinal database, and then you do visualization and communication. The topics include Python, database basics, what will be the skills, particular skills that are required for this. Understanding the uses of social media and using APIs, application programming interfaces. Machine learning, networks, record linkage, non-random samples and statistical inference, and visualization and communication. What is our focus of our center? And this is, I'm going more specific into a use case of science policy here. John Marthager was the head of PCAST, president, scientific advisor for the president in the White House. And in his science piece, he asked, how much should a nation spend on science? What kind of science? How much from private versus public sectors? All these questions are so important and so difficult to answer without actually evaluating the science investment. And taxpayers give the money to the budget gives the money to NSF and NIH, and then it goes somewhere. And what is this science? So science is not abstract. Where does it go? What is the economic output? What is the social output? And how we can evaluate it? These are questions that we ask. What is the conceptual framework behind what we do? It has 4 components. So there is a funding coming from the government. It goes to the institutions. The institutions employ people. People produce and use products. Funding also supports products. Funding pays for and is awarded to people. So all of these components, what it shows is that the complexity of the task that is in front of us is so difficult because everything is intermingled and everything is connected that we have to see this bigger picture, as we discussed, as in the plenary was discussed. You have to see the bigger picture, and then you can zoom in to whatever the practical solutions will be with particular tasks. So what are our tasks? We're framing them around 3, usually, but not always. So what is funded? Here we have to do research classification and do portfolio explorer. So basically, when you go to NSF, for example, National Science Foundation, they have no idea what's being funded. Okay, you have programs, you have NSF divisions, and then you have a standard taxonomy that is 30 years old. So they don't know what research is being funded and how you evaluate it from the point of view like some is interdisciplinary, how I identify it, and then you have to have particular funding patterns towards that particular part of research rather than the other one. Who is funded? So we can collect researcher profiles, we can do collaboration networks, we can figure out how ideas flow across space and time. And what results are being produced. These are publications, patents, altmetrics. Altmetrics is a new word. It's like Twitter, so alternative metrics. So you have Twitter, you have websites, you have blogs, all this kind of stuff. I'll just give you one use case. What we do with research classification. So science is always changing. You cannot just have a standard taxonomy that will always be there: physics, chemistry, something else. Then you have in 2000 the National Nanotechnology Initiative, and you have to figure out what is nanotechnology. So taxonomies are obsolete currently in the United States of America. The standard classification dates back to 1978, and it's pretty much have never been updated. Science-funded data becomes increasingly available, and this is very important. So one of the major points for big data is that you have more and more data that is available. You don't need to go to a library, sit down, and not leave anywhere, just sit there. But there is Star Metrics, there is NIH Reporter, NSF Award Search, Eagle, etc. And then you have research outputs that are also accessible not only via Thomson Reuters Web of Science, those bad guys who are actually taking all the scientific labor and put it into money for themselves. But you have open source, Microsoft Evgeny Search, Medline, USPTO, and so forth. So one of the processes that you can do is, one, just exemplify. So you download, clean, organize, and process the data. This is a very big piece. Then you choose, adapt, and evaluate the methods. So the ones we use are topic modeling, information retrieval, and natural language processing. And very important here, there is no out-of-the-box solution in big data. There is none. So you have to get dirty. You have to go and just put your hand into data and figure out what's going on. Run and compare results from various approaches, and very importantly, validate, which requires specifically designed statistical tests and additional data. Let me just quickly show you. So this is one of the projects that we have done for French Institute of Cancer Research. So this uses topic modeling. I'm sorry, it's very, very small letters there. But basically what it does is it takes all the award abstracts from this research project sponsored by Institute of Cancer Research. And it just puts them into bags of words, so-called bags of words, and it figures out where the words co-occur, probabilistic. It's a Bayesian computational algorithm. So it figures out where the words co-occur, and then you know the context, and it gives you statistically robust results as to how you describe it, what are the beans where you can put your particular research projects. And then you can use inference in order to understand what particular topic goes to a particular document. And then, also pretty small, but just this is what I'm showing this is a web tool. So this is the visualization part. So basically, we create the web tool based on our analysis. And this one tells, for example, there is a particular research project in cancer, and then you have the topics from the Helios topic model, and then you have the NIH topic model that is also inferenced, and then you can figure out where French Institute of Cancer Research belongs in the NIH universe. That is very important for international benchmarks and comparisons. One other thing is it's an ongoing project for USDA. So how do you find food safety and awards, for example? You just create, so this is kind of our home bred method. So you can use different methods, and this is coming to how do you validate what you found? This is coming to quality of your analysis. So you can use all those different methods, and one of the ways is you just create a Venn diagram, and somewhere in the middle you find that these are, for example, the food safety awards. But this is just to exemplify again the method. My last slide, conclusions. So today's tasks require more multidisciplinarity and innovation. You have to know both the root of the problem and the solution of the problem. The second one is big data does not make all traditional data and methods obsolete. You shouldn't throw away everything that you already know. You have to build upon that hire new people, just try to change your organization structures anyhow. There are no out-of-the-box solutions. Stata, SAS, all these programs will never help you with particular tasks. You have to get dirty, you have to go, you have to code, you have to use Python, any other language, you have to figure out how to do it. And that's not always easy. You cannot just, I push the button and that's my result. No, it never works like that. Validations are critical. This is what we have in computer algorithms. They never have any validation tests there. That's why you have Google flu shot problem, where they just, they predicted 3 times more than it should be. So validation and statistical validation is very, very important. And continuous learning, just never stop. Start coding, start figuring out how to do it.
Thank you. So now Dahlia Remler from Baruch College will talk about implications for PA and public policy education.
So, first of all, like Evgeny, I actually changed my talk from the abstract. I know a lot about how to teach research analysis and what to teach, and I know what a lot of other different places and programs do, but I've only recently started learning about big data, unlike the other people. I want to thank all of the preceding speakers for sending me advance notice about what they were going to talk. And although I have a lot of suggestions here, I want to emphasize that I'm particular raising questions. I think a lot of things are in the early stages. Okay, so what I'm going to do, even though this audience knows a lot about research analysis for MPP and MPA students, I want to remind you of some things that I think are particularly important as we try and sort out what we do to those programs. I'm going to focus on changes in what we teach, really, rather than how we teach it. And 3 parts are new stuff we need to teach, old stuff that's now more important, old stuff that's less important. I'll discuss the issues of prioritizing. We have time constraints. How do we prioritize? Okay. So, basically, all MPA and MPP programs have some form of research analysis requirement. The courses vary in name, but they also vary somewhat in content and emphasis. Some occasionally you'll see places that only teach statistics. It's relatively rare. Some places teach a lot of qualitative, some places teach none. Some have quantitative methods besides statistics, operations research, things like that. Others don't. Some places teach data collection, some places don't. Okay? What should we be doing? Is there more variation out there than is really optimal? You also see variation in how many courses. There's always at least 1. There's usually 2. Sometimes there's 3 required courses, semesters. Is that the right amount? And does big data change the amount of courses we should be having? I'll talk mostly about the required courses. I want to talk a little bit about capstone and briefly mention, what does this mean for more advanced research analysis courses, specialized courses, some things like Minyoung was teaching. Okay, so what are the challenges? And again, this is not new to you. So as everyone knows, the very diverse quantitative backgrounds of our students are an enormous teaching challenge, and the sequential nature of much of statistics makes it a really big challenge. Now we may also be dealing with a very diverse IT background. Some of the employer panels mentioned, we learn from the new incoming people. Well, some of the students know way more than the faculty, but not all of them do. So we have to manage this IT diversity as well now. Diverse motivations, career stage, but again, the limited time. Not just limited courses, but the time our students have and their other obligations. And then finally, and this I think was mentioned several times in the employer panels, most MPAs, more MPPs, don't become researchers or analysts, but everybody is a consumer of research and analysis and often a commissioner. One issue that's been raised is, will almost everyone become a certain amount of analysis as we're dealing with constant data flows? Do we need to think that there'll be more production of research and analysis by a much larger share of our graduates than in the past? So what should we get? And I think, again, the Employer panel really highlighted a lot of these issues. The number one goal is that we produce good consumers of research and analysis. Very few of our students will do an analysis like Evgeny did. All of them will have to read analyses like these, spot weak and invalid conclusions, extract and apply relevant, valid conclusions. The quantitative literacy that I think was also discussed by the state budget director, again, maybe not the fancy techniques, but everybody needs to look at this and extract and get sort of basic quantitative literacy as part of their ability to do those first things. Commissioning research, well, there'll be different kinds of research to commission. Posing questions, purpose effectively. Performing, so more quick on the fly analysis with data being constantly available, as well as formal traditional research. So again, sorry, I went the wrong way. Okay, we can't just say do this, add this, and this. That is not possible. So new stuff from big data, and again, I think previous speakers really showed a lot. Existing qualitative data, tweets, YouTube videos, websites, just the volume is staggering and the velocity is staggering. So coding, converting that massive amount of qualitative data out there into quantitative data. And that's going to be a much harder and messier kinds of things. Analyzing. So this isn't your traditional qualitative data analysis where people had very small n and they really could listen and read and things like that. This is a much more massive kinds of things. And I think the world is still learning how it's going to be analyzing. I don't know what is appropriate for us to add at this stage in terms of our teaching, but that has to be on the time horizon. On the horizon. I want to briefly mention, and I'm going to come back to the issue about inferential statistics and the very large amount of time and effort we teach about formal inferential statistics. A lot of the data we have, and this is true now, is census data. It's not a sample. And often the theoretical foundation of inference is problematic. The econometrics usually is specifying a sort of functional form. Apologies to those who aren't as into the technical things. But I think, a lot of thinking about that is even more thinking about what do we mean by inference, putting it on a foundation. Data visualization. That is a skill that probably all of our students do need. And I know that I, for one, have a lot of catching up to do, and my observation is a lot of other faculty do as well. And so I think that's something that needs to have a much greater emphasis, and we really need to improve our game. So here's this isn't a big data project, this is a fairly conventional one. This was tweeted out by John Graves, and I thought, wow, that is a great image. So just new ways of visualizing data, training people to do that, that is so important, and that is something that all of our students need. Knowledge about big forms, about big data. So, it was always a message we gave to people. You really have to know, where did this data come from? What were the incentives of the people who collected it, or how was it collected, where does it come from, what does it mean, to really assess its validity and reliability. That, as I think we've really seen, has now gotten a whole lot more technical and complicated. So, this has gotten a lot harder. I would say there was raw data, so in that sense I would disagree with Trevor, but what I mean is, we all live on the internet and we leave kind of information droppings along the internet as we live. I think of that as raw, among the raw forms of data. And then after that, Trevor's right, everything else we do is a choice. So what's out there? How can we extract it? You know, if you're pinging some, portal or something, if I'm trying to ping healthcare.gov, all of that. How this stuff is cleaned and merged. Again, every case is going to be different. I appreciate the image of, digging in and getting your hands dirty. But at least all the students need to be able to sort of listen to a description of that and figure out what's good. So new forms of analysis, I put questions because I think it's too soon to figure out what you want to teach in our master's programs. But there's machine learning, there's computer science algorithms, and we're all going to be seeing papers and reports that have this stuff in them. So what do we need to teach? Everyone is going to be consuming these new forms of analysis. Okay, so old stuff that's even more important, and Trevor really emphasized this, Evgeny also mentioned this. Correlation versus causation was obviously extremely important in the first place, but distinguishing description, prediction, a causal effect where you have one specific independent variable or program, or maybe a couple, on well-defined outcomes, versus the whole explanation of a really complicated system. So being really clear about the distinctions between those things and both what you want to know and what you're able to know from a particular form of analysis. Related to that, theory and mechanisms. So I think, analytical thinking was heavily emphasized in the employer panel. So my favorite tool are path models for people to think about causal thinking and to always have this models in your head about what's going on. So the idea that, we don't need theory anymore, the sort of hubris of the very early big data, I think everyone agrees, no, that was wrong. Measurement. What do you want to measure? What is its purpose? It's not just the data. You have to figure out what you want to measure, how you're going to use it, and when you do that, you have to, the validity, concept versus actual measure. Reliability is very important, but I think validity is even harder in these contexts. And I think the Google flu trends and their initial great, and it's a great thing. Don't get me wrong. The potential here is enormous that we can look and see people's search terms and use that information. But Google changes its algorithm constantly. People change their behavior. People change their behavior even in response to Google flu trends. So the validity of measurement is a problem there. Not as mentioned is the desired population of who you want to measure thing versus sample, and I put sample in quotes because they're often not samples, but they're still who or what gets in your data compared to who or what you want in your data. So those things are, continue to be important, but I think are even more important with all this complicated data. So going back to the correlation versus causation, the time trend correlation is a particular problem. Many of you probably saw the recent New York Times big data, and I think one of my favorite graphs is that one. You can have almost any trend over time, and you can see how often people do something, how much they do something. So, Googling things has been going up. Anything else that's been going up, you can correlate with Googling things going up. So we see, and this is the kind of thing which every student needs hammered into their head, and hammering is like, but figuring out for themselves to talk about the active learning again and again and again, so that it's almost instinctive. Okay, old stuff that's more important continued. Data management and data structures, those were important, but they got a whole bunch more complicated. And I think data structure, so from an education example with online learning, you have everything that the students do on their online learning. You can track what they do at the chapter level, at the question level, repeating questions. the complexity of the data structure means that students really need to get, even if they don't know the complexity of the data themselves, when it gets analyzed, what's being analyzed, what's being used. Data analysis, I'll come back to inference, practicing with actual data, just to get that feeling, that's been important. I think it's even more important. The intuition about things like overfitting, statistical significance, the problem if you have a ton of data, basically you can get statistical significance with anything, no matter how small. So the basic intuitions about these things, multiple comparison problems, because again, you have so much data. Everyday analysis, just looking at data, seeing patterns, interpreting. Old stuff that's less important. So I say, either we're going to add more courses, or we have to cut some stuff, or shorten some stuff. So what is less important? I would argue that a lot of what people spend time on, typically in inferential statistics, we don't need. You really need the idea of hypothesis testing, and making sure people do not misinterpret p-values and the difference between statistical significance and practical significance. All of that's really important. But, do you have equal variances in your t-test? What are the theoretical foundations of this? And I would argue a lot of what's done in some courses in probability. Basic ideas of probability, absolutely. But a lot of the technical stuff, we spend a lot of time on statistics, which quite frankly, many students, 1 month later, never mind 10 years later, it's gone. So I think that so I think if there's a place to cut, it's in what we're doing with inferential statistics. So now to be provocative, I would really like to argue that everyone should add a required course in research and analysis, as well as having more advanced courses, lengthening the capstone as was added. And, to avoid the problem of people saying, oh, what I do is most important and you should have more of that, or that, I'll be very aggressive and controversial and say that I'm an economist. I would cut economics from our core to have another third research and analysis course required, okay? And I think that would be particularly okay if we put a lot of the kind of logic model, mechanism, causal thinking, really sort of analytical thinking into the research analysis course, material that often occurs currently in economics courses. I don't want to cut the economics course. I'm not advocating that. David, my dean is back there. But, if you made me choose and you said you can't take from courses that other people teach, I would argue that research analysis has gotten that much more important. Okay, so more data analysis, less inferential statistics, and particularly less technical inferential statistics. And again, I'm saying you should do this, but I think I'm raising questions. I think a lot of this is open. I'm interested in people's reactions. Data visualization, if there's one thing I feel very weak going into the next time I'm going to teach statistics, it's that I'm not qualified to teach that to my students, and I really need to be. The old skill of knowing your data, which was always important, just got a lot harder. In principle, it's the same. In practice, it's a lot more difficult. The correlation versus causation in theory are still very important, despite all the hype. Faculty, we're going to need to learn. So going back to the issue of the capstone, students should be able to do capstone in which they scrape data off the internet. And, how are we going to manage that? Who is going to provide that support and that knowledge? We're going to have to figure things like that out. And who is going to teach more advanced courses, or will we send them to another department? How is that going to work? So basically, I think that both Trevor and Minyoung, they're both right, okay? The hype may have been overdone and wrong in some of its detail, but this is an enormous detail. The quantitative change in the amount of data, the messiness of data, and the speed of the data the quantitative is big enough to be qualitative, and it is a very big deal. Okay, so I think, lots of questions remain about what to teach. Should we cut from required research analysis, or do we add some courses?
So I thought we would invite the panelists to come sit at the table, and we started about 10 minutes late because the opening session ran over, so that would still give us about 15 minutes for some group questions. And so maybe you could just address your question to the author. You might want to identify yourself, just so they know who you are.
I'm Baruch from the Air School at the University of Chicago. I'm actually teaching two of the classes that Evgeny showed on that AIR is doing. Most of the faculty who are teaching those classes are from the University of Chicago. And we combine both, it's being taught by both social scientists and computer scientists. So the question of whether or not we combine these tasks, these different areas in the same person, or we collaborate with computer scientists and social sciences is a big question. We've started, we'll be talking more about it at 3:30 today, we started a Master's of Science in Computational Analysis and Public Policy in the Public Policy School near Chicago, and we're the joint program with the Department of Computer Science. So they're all going to get Python, C, Java, Hadoop, MapReduce, a whole sequence of programming classes, data analytics, data, but it's not we've taken out kind of a lot of the political economy, political science classes out of the MVP. They're still getting micro, they're still getting stats, they're still getting econometrics. They're still getting one political science course on organizations and one on decision making. So we've combined those two. It's not an MPP anymore, it's not a Master's of Science class, but it's a hybrid of computer science and public policy, and it's also a hybrid of faculty for both the public policy school and the computer science school, senior faculty teaching these classes. And we're going to combine those. So there's two different, our biggest issue is that there's two different languages, two different jargons, two different cultures. We spent this past year having a seminar where we brought the two faculty together. We hope these things come together in internships. We already have 40 organizations that want interns. We have 15 students the first year. So there's a huge demand for this. We initially started a program because of the demand from the city of Chicago, people who could do both, who could understand public policy, and as well as could do Python programming, and then text mining and all the things that went along with that. So it's really, I think my question is whether or not, or my question is whether or not we can really do both of these things in MPP and MPA programs, whether there's still a utility for what's happening in MPP and MPA programs. They're getting jobs. So are we just creating a new type of person who can operate in the public sector or in consulting firms or AIR and do these types of analysis?
Would one of you like to respond to that, and then we'll take another question?
I'll just respond briefly. I mean, if you're talking about people who can really do this, no. That's, there may be the rare MPA, MPP, but if you're talking about people who need to be able to intelligently respond to those analyses, absolutely.
Okay. Sean,
can I just...
I think we want to move along and let
a very brief comment.
Yeah, go ahead.
Yeah, I just say that because I have experience with those very diverse courses coming together, and many students are really discontent with because they don't understand. One people say one jargon, other people say different jargon, so it just doesn't come together. Therefore, it's very important to integrate this somehow and maybe bring faculty together to talk each other rather than all the students.
Sure. So my name is Sean Tanner. I'm a doctoral student at the Goldman School. And so my question is about causal inference. And I think so far I'm in 100% agreement with Trevor. So there's one case that I know of, let's say Raj Shetty and his colleagues have used big administrative data to test sort of the exogeneity assumptions that we were layering on models of how we evaluate teachers. And and in that sense, big data sort of helped causal inference. But I'm wondering if anybody can name one instance of where big data very specifically has assisted our causal inferential strategy in a way that would make it into JPAM or the QJE, that would meet our rigorous standards.
It depends what you mean by causal inference. So just to be trivial about it, because I'm the person here who knows the least about big data, but one of the examples I made into a New York Times article was, identifying sort of who and where dumping of oil that was clogging up the system goes. So if you mean the sort of traditional, do small classrooms work? I can't, but if you mean what was causing something to happen in that sense, yeah, I mean,
no, I mean the traditional.
So let me respond to this. Just that I think there's numerous examples in the New York Times. I believe it was Wednesday morning. There was a story where data was taken out of the immediate capture database of early enrollees under the Affordable Care Act to give early distributional analysis. There are numerous papers where people do things like they go out and they access data coming in off air pollution standards, correlate environmental hazards off opportunity data with public health problems. There are entire fields where maybe we used to look at how disadvantaged minorities over the business cycle, how their employment cycles, but that was based on averages, not on transitional analysis, but the availability of very detailed individual level data over time that's through amalgamations of massive administrative records that lets you look at these things. And there are examples of all these things, not only in the JPAM, but the AER and the QJE. And so I think that that's part of the reason why people are intrigued with this.
My name is Steven Chivoni. I work at the Federal Housing Finance Agency. I just want to know if there's any books you could recommend on either coding, data visualization, and I guess theory of data, like collection or analysis.
If I get your card, I'll give you the name of the book that I just read on data visualization. It's fantastic. It's published by the
Thank you.
There's a recent paper published by Jonathan Swabish in the Journal of Economic Perspectives on data visualization. JPAM is actually running a special section of papers in the next 6 months on data visualization and policy informatics, how to use thinking about visualizing large-scale data. So it'll be more on that. But Jonathan Swabish is a journal.
And what was it, the journal?
JPAM Journal of Policy Analysis and Management. Other questions from the audience?
Yeah, maybe I'll just a quick point, and largely make a response to Trevor, even though it relates to all the presentations. But in contrast to 100%, I'd say I'm 90% in agreement. And the way I think the interpretation, the way we take it in this environment is probably that big data analysis can be seen more as a complement to the traditional work that we've done more than as a substitute. But anytime I think about a critique like this, I'm always reminded of a jazz song from the late 1960s called Compared to What? And so I always think of in terms of counterfactuals as a researcher. And the implicit counterfactual a lot of times when we're discussing big data is, well, we've got an alternative out there. It's a nice, clean data set. Or we can go after the big data. But a lot of times that's not the case. We don't have a data set that's an alternative. So we're only web scraping because there's not a nice, tidy database already out there. Another example of a counterfactual is, well, it may be expensive to go out and collect the kind of data set that we want. And so we work more with the data exhaust, as you call it. The analysis of the Google flu indicator is a good example of that, where there's been a lot of analysis of that versus the CDC data. If you put those two in a horse race, and ignore the costs, there's an argument about there about which one will outperform the other. But once you insert the costs, it's a very different discussion. The Google flu indicator obviously has a weakness, as we've talked about, but in practical terms, the margin is free as well. And so it may still be in the interest to focus on that as a measure, even though there's a, we've got existing some more expensive alternative out there that's outperforming the companies. The final point I'll make has to do with interpretation. Because as you point out, interpretation is still an important part of the picture. I think everybody made that point. But the premium on interpretation varies from one public policy setting to another. So in a public policy setting, and one of the public policy settings where that's important with this regard is in performance measures. So if we're trying to explain the factors that lead somebody to have a positive employment experience, then we really worry about the causality in a model of what generates positive employment outcomes. But in contrast, what we want to comment on is how do we vary a performance standard for a local area given the characteristics of the population served in that local area? Well, I don't care so much about causality in that case. In fact, what I'm doing is largely prediction. And in that case, if I've got an alternative that's built on correlation, I might prefer that. Even if it is expensive to produce in that case, the reliance on correlation may be more effective in that case. So that's just two kind of mildly contrary points here.
I just want to say that what makes a good algorithm, a good method, is that you can actually ask these different questions to it and optimize it whatever you want. So, for example, I work with random forest, it's a machine learning classification technique, and you can just throw in all the variables that you have. You just have to convert them into K-card or into digits, and then you play around and you ask different questions and you get different results. And then you get accuracy scores, you get all this, like what is important, what's not important. But this makes a good method. If it is statistically robust and it has like not only quantity but also quality measures, how you assess the quality of data. You can get millions of records, but you have to have tests to say that this is good data or this is bad data. And not only when you get to the analysis, because this will be expensive when you already get to the analysis, but if you can say in the entry, in the input, that this is good data and it will work for you, that is very important as big data.
Just two very short comments there. One, I think coming back to something that Dahlia brought up in her presentation, I think it's really a question of validity, right? The appropriateness of use of the data. As long as you're aware of all the concerns that go into it and you take those into account, there are certainly times where I think just looking at prediction is sufficient. And I tried to address that a little bit in this quick presentation. And the second thing I would say is we want to be very careful, I think, about the street light phenomenon. We don't want to go looking for our keys under the street light because that's where the light is.
So I think we should break for lunch. Sounds like everyone else is. Well, we thank the authors.